Not for today.
Hey, Thomas.
Okay, hello. It's time to start, not time to talk.
Hello, Thomas.
Wow.
Come on.
He took his 2-day vacation.
What?
Why y'all are really?
Actually, I'm sick. I'd rather not.
I appreciate that. However, you missed the test that went on this quarter. Yeah. Okay, so chapter 7. Okay, chapter 7. We are still dealing with dots. We are still dealing with lines.
Yeah.
What we are not going to deal with in this chapter is trying to create a circuit or a path. That is gone. Okay, so we're going to do something called networks in this chapter. Okay, vertices of your networks are now going to be called nodes or terminals. With nodes. Probably because you have, because this is more real life.
Don't believe it for 1 second.
Okay, your edges of your networks are now going to be called links. And they are the connections amongst your terminals. Okay, so this chapter actually gets into telephone lines, cable lines, and all of that kind of stuff. Okay, so a telephone line doesn't have to create a circuit. It just has to go from the main source out to your house. Okay. So we have to reach out to all the points in this chapter, but we don't have to close it off. So our job and your chapter theme is finding optimal networks that connect a set of points. There we go. Okay. So we're going to connect all of your vertices or your terminals, but we don't have to create a path or circuit. Okay, and because we're looking for optimal, I'm still trying to find the shortest way possible. Okay, the cable companies and the phone companies are not going to sit there and dump more money if they can save it. Okay, they want to make a profit. So their job is to figure out how to do this at the smallest cost. Questions?
No. Less money, more power.
Pretty much.
Just
I mean, if you think about it, every company, their goal is to make a profit. So the less money they can spend, the better off they are. But they've got to keep up with the times. They've got to upgrade. I mean, when I got my cell phone, I'm pretty sure we still had 2G when I first got a cell phone.
Really?
We're now up to what, 5G?
Remember Blackberry?
Okay. Blackberries were the bomb. And I think they called it a chocolate. It was one of the ones that had this little like dial thing on the front and it slid up into the keyboard. And I mean, I had one of those old, has anybody seen Saved by the Bell?
Yeah.
And you saw the old Zach Morris cell phone?
Yeah.
I had one of those.
Like the one you have to like.
Oh, no, my grandma had a rotary phone. That's a rotary phone where you had to sit there and go 1,
Yeah, my grandma had one of those.
2.
My grandma had one.
Okay. I mean, it's what we use. I mean, think about it.
Some people
Back in the day, you were attached to the phone by a cord if you wanted to talk. You couldn't talk in your car. You couldn't, I mean, things have upgraded. So as they upgrade, they don't want to spend all this money that's gonna put them in the hole. They wanna spend the little amount as possible and still give you the service that you need. Amen. Okay, that's the whole point. Let's make some money. Okay, so this is an example of a network problem that you might see. Bring this down. Okay, the weighted graph represents a system of roads connecting buildings of a company's headquarters. The company is planning to upgrade its fiber optic cable through underground lines connecting its servers. The weights represent the cost in millions of dollars to upgrade. Okay, the goal for the company is to find a network that utilizes the existing network of roads that connects all of the buildings together and has the least cost. Okay, so basically what you're going to want to do in this chapter is you're going to want to look at this graph and say, what is the smallest number up there?
1.8.
Kind of like cheapest link when we start. So 1.8. 1.8 will take service from D to B.
2.1.
2.1 is my next one. That connects C in. 2.2. That connects A in. Okay, now stop. Remember, we do not want to create a circuit. So she said 2.4.
So that can't.
We don't want to use that. We don't want to close it off. We don't have to. 2.5 is the next one. Has every dot been given service?
Yes.
Yes. You're done.
Oh,
this is easy.
Okay.
I like
You're
when I
done.
name my school.
Yeah, but-
That's all, how much harder does it get?
That's it.
Yeah, two big lines.
Okay. The hardest part is going to be, there is a section in this chapter where you have to, I give you words, like I'll tell you, your graph has 5 vertices and 4 edges. Is this always a tree, sometimes, or never? Okay, we're gonna talk about properties, that's gonna be the hardest part of it.
What is a tree?
We're gonna talk about it. What you actually just created is a tree. You just created a tree. Okay. So we gotta talk about some properties that you'll see in a tree. Okay, so there's some key terms that you need to know in this. One is a subgraph. A subgraph is the edges have to come from the original graph. So, in other words, a subgraph is a small part of a graph. It's just like taking a graph and cutting off sections. That's now a subgraph. It's a smaller part of your original. Okay. So if you had a chocolate bar and you broke off a piece to share with the one,
Why would I share with the one?
Rude.
I don't know.
I'd share it with you, not with the one.
Oh, okay. So you have a chocolate bar and you break off a piece and you share it with me.
Okay.
That smaller piece is a subgraph of your chocolate bar.
Okay.
He don't want to share with you.
I'm gonna share with you.
A span. A span is a type of subgraph. Okay, but what is the difference is a subgraph doesn't have to have all of the vertices of the original. If I'm drawing a span, the graph must include all of your vertices. Okay, it doesn't have to include all of your edges, but if you're drawing a span, you have to have all of the vertices of the original graph. Yes.
I thought that you changed the edges to length and that's a common.
What?
Physical confusion.
So yes, don't read too much into that. I'm just saying, if they say A to B shares a link, that's an edge.
To get out of the-
Don't read too much into that. I see where you're going, but don't read too much into that. I just want you to be able to identify if I say terminal A, you should know that that's vertex A.
I didn't say
So
that.
this is the skin, because all of them have something.
Mhm. So Thomas just said this graph that I drew up here, I'm just gonna write it down here. Give me a second. A, E, take a nap real quick. I'm not gonna be that slow. D, bam, we did this, we did this, we did this. So this is the graph. Let me bring this up
It's the
actually.
same graph for everything.
This is the graph that we just drew when I highlighted all those smallest edges. This is considered a span with 4 edges because it has every dot of the original graph, but it only has 4 edges from the original graph. So they would call this a span with 4 edges. Remember, a span just has to include every dot. So A's there, B's there, C's there, D's there, E's there. It does not have to include every edge.
I would always say I thought it had to come from the same spot.
Don't have to come from the same spot as long as they're all are connected. So think about it this way. You can never ever have a disconnected graph if you have a network. Okay, everything has to be connected. And again, we're looking for minimal. So we're looking for the total weight of the network must be as small as possible. That's my job, to make it as small as possible. Questions? Okay, so we're gonna practice drawing
No.
spans
No.
and subgraphs. Yes, yes, yes.
No.
Okay,
I already got the example for example 1.
oh yeah?
Yep.
So, this is my original graph right here. A, B, C, D, E, F. They want us to draw a subgraph that has 4 vertices and 6 edges. So, basically, they want a piece of this graph that contains 4 vertices and 6 edges. What piece of this graph do we want?
It's a big B
B,
and E,
B and E.
Oh, B and C.
F.
A, B, C, D, E, F.
Whoa, whoa, whoa. Stop. Stop. Rodrigo, enough, please.
Would you use B, C, F?
I need to pick a piece of this graph that has 4 vertices and 6 edges.
That's B, E, F, and C.
Okay, that's going to be this section of the graph. Right here.
Yeah. You said B and E, what you mean? That's the whole, you gotta get.
I was saying and C, and then she said stop.
Well, no, because somebody was saying A and so B, C, E, and F contain 4 dots and 6 edges. Because there's an edge that connects B to C, one that connects C to F, one that connects F to E, one that connects B to E, B to F, and E to C.
So graph C by
I didn't even know they were out
I ain't even
there.
know.
I feel like she was the only one that really paid attention.
Was it frustrating?
Okay. A span. A span has to have all of the dots, which is why they have 6 drawn here. So we've got A, B, C, D, E, and F. Okay. A span has to be connected. So I need to pick 5 edges from my original graph that would connect all 6 of these dots.
Everything is circle on this X.
Okay, so you said you want to do A to B, B to C, C to F, F to E, and E to D. Okay, so Alicia said I can just get rid of this line that connects C to E, B to F, and B to E. That's one way to do it. Okay, I could have, instead of using this one, I could have used this one.
Wait.
It's still 5 edges, and it still connects every dot into one graph. Okay?
I would do that one.
Yes, that one works too. Okay, you could have left that one off and you could have done this. As long as your edges were from the original graph, everything's connected and you used 5. So one thing you can't do is I can't do this. There was never a edge that connected A to D. So that is a no-no. You cannot connect anything that was never connected to begin with. Okay, so keep that in mind. Okay? This one down here, they want a subgraph of 5 vertices and 4 edges. So you need to pick which 5 dots we're going to use. Which one do we want to not use? Let's do it that way.
We don't want to use that.
D.
You don't want to use F.
D.
Hold on, Thomas said he doesn't want to use F. Let's do that. A, B, C,
The water
D.
question.
and E. Yes, the one.
Yes, you're Lewis.
Oh, I thought you answered. You answered the question.
Oh, I answered it? Okay. Okay. You could have used F and not used E. You could have used everything but A. It doesn't tell you which 5 you had to use. Okay. So now, again, I need to pick 4 edges from this graph to connect these 5 dots. So,
C.
you said what?
C.
C to what?
B.
C to B? Okay.
A.
A to B? That's 2.
C to D.
C to D.
Why would you do that?
A to D. I'm A to
You
D.
can't do that. There's no line that connects C to D from the original.
A to E. I'm B to E.
Hold on, because I'm getting too many
What?
things
B
here.
You can either do B to E or C to E.
Let's say B.
Okay?
Choose one.
B to E or C to E. You've got to pick one. Pick B to E if you want to do B to E.
E to B. I mean D. Sorry.
And then E to D. Okay. So, like Rodrigo said though, I can use C to E or I can use B to E. It didn't matter which one I chose. Okay. Questions? Not too bad yet, right?
No.
I'm so cold.
Because it's freezing outside and that's still blowing out cold air. Okay, this middle one says I want a span of 6 edges. So that word span tells me I need all my dots. A, B, C, D, E, and F. They want me to use 6 edges now to connect these.
A to B, B to C, C to F, F to E, E to D, and then just put B to E.
Bam. That works. A to B, B to C, C to F, F to E, E to D, B to E.
Or
You
can
could have
do-
switched out one of those for C to E or B to F. Okay, yes, yes. The last one, they want a subgraph of 6 vertices and 5 edges. So I need 6 dots.
Just take out.
What else could I call this instead of a subgraph of 6 vertices?
A graph of 6 vertices.
A span.
This is a span. A subgraph of 6 vertices in this instance is also a span because it uses all 6 vertices. Okay?
Just do the same thing except taking out B to E.
So,
I see that.
do the same exact thing.
I can go to B to C. I meant.
No, take out B to E.
Careful, we only want 5 edges.
That's why I said take
Take
out
out
B
B to E.
to E. If you take out B to E, it's gonna be 5. A,
Oh,
B.
you're talking about this one.
Yeah.
I was going back to the original. I'm like, no, that's still too many lines. What are you talking about? So, Rodrigo says I can use the one from the one we just did and take out B to E. Okay. Subgraph, 6 vertices, 5 edges. Questions? You drew yours differently? 1, 2, 3, 4, 5. That works. We've pretty much got one more page.
Wow.
Pretty much.
Tree. Okay. So a tree is a special network.
That's a Christmas tree.
It's a Christmas
And the
tree.
ones with the less, the two, but they're all connected to one dot.
There's a lot of old wood.
No way.
The old wood in the back.
Not my fault.
The old wood. Got old wood.
All right.
Oh, this is connected.
So here is your formal definition. A tree is a network, which means it must be a connected graph. Anything that is disconnected is automatically not a tree. Okay. It also has to have no circuits of any length. I'm not saying that the entire graph has to be a circuit. I'm saying there cannot be any closed off circuit section in your graph. Okay. So we want to look at these 8 problems and determine it's a tree or it's not. Take 5 minutes and see if you can identify before we talk about it.
Question
Yes.
on A, that's what's supposed to not be connected.
That's not.
Yes.
Okay, that's not a graph. I mean, not a tree.
Right.
Thanks. Can I just put no?
That's fine. You can put no and yes. You can put tree and not. I don't care.
Can I put not?
As long as you know the difference between what you're putting. So look at each one of those graphs and see if you can determine it is a tree, it is not a tree. Again, a tree has to be fully connected and absolutely no circuits of any length. Which means your graph can't have loops. Your graph can't have multiple edges. Your graph can't have a triangle in it. Princess, can you please pick up your head and participate because we got stuff to do today.
No way.
Would that be a no? Thank you. Not connected, or would it be yes because it's connected?
Because that's connected down there, it's all one big piece.
Okay, you said that's what you
How many no's are there? How many no's are there?
That's one tree.
That triangle is on.
Obviously, none of these.
Yeah, but we're so.
It's on.
But that's,
Last one.
That looks like-
your lines go from dot to dot.
That's not close.
So while I understand, yes, that's gonna trip you up.
I had yeah at first,
How
but
many no's are there?
That looks like a tree.
you said triangle.
1, 2, 3, there should be 4 no's. 4 no's, 4 yeses.
That's funny.
Hold up.
Oh, yeah.
This
Run
one,
that back.
Oh, yeah.
Run that back.
This one.
Uh-huh. 4 no's, 4 yeses.
Run that
This
back.
one.
Oh,
Is this right?
Is there a space? There ain't no board on the screen.
Yes, there is.
It's bad. You just don't know about those.
There's something wrong with yours.
It's not right.
4 no's, 4 yeses.
Wait, you said if there's two pieces and they're not connected, then
You've got 2 of them mixed up.
Connected.
She knows that you.
I did now.
You got two mixed up.
I think it's her job.
No, that's what's a yes. That's what's a yes. Yeah, 'cause she said it needs to be like different.
If you got triangles, it's a no.
One of yours is wrong.
I don't see.
Oh.
You got two.
That's what she's telling.
I can tell it's a trip.
I don't see.
What?
You got two mixed up. Wait till I show you which two. Because it's pretty much the same two for everybody right now.
What does it have to be?
Yeah, Miss Smith.
Wait a minute, wait.
Oliver's got it.
I got it too.
Oliver's got it. Come on now.
It smells good though.
Oh, yeah, there we go. We fixed that.
Oh my god, I see it.
I don't see it.
They all got each other.
I see it. It's just, and that's.
Yes. And you got a couple
Bro, I wish I would've
disconnected
had
these
this
ones.
class.
Yes.
Miss Smith, Dewan has a question.
The one has a question.
Yeah, for you. More of a statement.
This is
Whenever we were in the community, I'll show you how to look.
What?
I see it now. Thank you for that. I didn't see it.
What?
Yeah,
But they're not supposed to not, because I already had his class. And then the second grade, American history, two history gentlemen. Third, June.
You're not gonna say one more thing.
Well, I don't want to take it out because it's my whole year. I'll go for one day and it's trash. I'm like, I'm giving the class next. But this semester they put me in my class and I told them that I already had it. Switch it out.
All right,
But then they put it.
let's look at this. What is A?
No.
No. Why is A no?
It's not
Disconnected.
disconnected.
It's disconnected. There's two components. It's disconnected. What about B?
Yes.
Yes.
That's a yes.
No.
C.
No.
Why?
That's a circuit.
It has a circuit.
Oh, okay. I was just gonna say
Okay.
triangle, but-
It has a circuit. I'm sorry, D.
No, I mean, yeah.
Yes. Yes.
D should be yes.
It's a tree. It's a tree fish.
E.
Yes.
Is
Yes.
Oh.
Okay. E is yes. F.
No.
No.
Disconnected.
E in terms of a network. Okay. G and H.
Yeah.
D is no.
Yes and
Yes.
no.
Somehow.
G is yes.
It's a tree.
H is no.
Can you explain how it is?
Okay. So G, be careful. Your edges go from vertex to vertex. So I heard this is a circuit, Miss Smith. No, it's not. Because your dot goes from here to here. You can't stop and change directions halfway through the line. So, when you trace this, it doesn't actually close off. Okay. H, however, just because this is twisted, watch what happens. If I start here and I trace this out,
It ends up that-
it's a circuit. So this circuit is hard to see because it's kind of twisted.
So
those will be
G,
on
if
test,
G
right?
was looking more
Okay.
3D model, it would be so much easier.
Listen, there is a pattern and a way to determine whether it's a tree or not a tree instead of just looking at it.
That's what I'm looking for, the cheat codes.
The cheat codes, right? It's like, oh my gosh, you just brought me back to the PlayStation days.
No, that was like.
Up, down,
in the
left,
NES.
Right.
No, it's up, down, left,
That was in the NES.
That was with Cortana.
No.
You all talking Mortal Kombat?
Yes. I am. Katana's in Mortal Kombat.
All right. So, what does your next question say?
Is there a relationship?
Is there a relationship between the vertex and the edges? So, let's look at each one of these. How many vertices are in graph A? How many dots do I have in graph A?
7, 8, 9.
There are 9. How many edges are in graph A?
7.
7.
Oh my god.
Okay.
Still mine.
Hold on. No. Don't go there yet. Vertex. How many in B? 11. How many edges?
But one's odd and one's even.
Vertex. In C. 5. Edges.
5.
5. D. Vertex. 6. Edges.
5.
5.
Oh my god.
Vertex. In E.
7.
7. Edges.
6.
6.
Oh my god.
F. Vertex.
Not even touch that.
1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Here, vertex. 8. Edges. 1, 2, 3, 4, 5, 6, 7.
Is this just a coincidence?
Vertex. 1, 2, 3, 4, 5, 6, 7. Edges. 1, 2, 3, 4, 5, 6, 7. Okay. Look at every one of those that you
It's always
said
one less.
yes.
It's
When
always
they're
one
the
less.
trees, they're always one less. But when they're not.
Every one that is a tree,
Oh.
however many dots you have one less edge.
Oh my god.
Anything
Oh
else
my.
is automatically a no. So, A, we had 9 and 7. They were 2 apart. That's a no. C was 5 and 5. That's a no. F was 11 and 13. That's a no. H was 7 and 7. That's a no. That is a guarantee, not a tree.
Oh my god. That makes so much sense.
Okay.
Opposite either.
So it doesn't matter whether it's even or odd.
I'm saying both of them were, you know.
Well, I mean, every tree's gonna have an even number and an odd
I
number.
mean, like, they're the same number.
Yeah, they're the same. So no.
So if they're the same, then it's a no.
If they're the same, it's a no. If the edges are 2 less or 3 less or 4 less, it's a no. If your edges are more than your vertices, it's a no. Flat out, no argument. Okay. So, is there a relationship between the total number of edges and vertices? Your edges are 1 less than the number of vertices. Okay, your edges are 1 less than the number of vertices each and every time. So let me actually go, I'll come back to that page in a minute. Let me actually go back here. Take a look at how many dots you had in this picture. 5. When I drew the network, how many edges did I use? 4.
4.
Ooh. So if you're given a graph with 7 dots, you automatically know I only need to highlight 6 lines.
I have a question.
Okay. Yes.
Why don't you tell us the cheat code to start?
Right.
Because I like to make your brains work.
Actually, I think just
That's not how
looking at
life
it is a
works.
little bit better than.
But that's how life's going to work. Nobody's going to just hand you answers. You
No,
actually
I
have
didn't say hand me. I said hand me the cheat code. The simple
You
way.
have the cheat code that money.
you have to discover the cheat codes.
But you
I
just
mean,
gave it to us.
If you buy a game, are they going to say, hey, here's the cheat codes and put it in the game? No. You got to Google that crap.
Now, some games do.
You got to Google that crap. They ain't giving it to you.
Actually, no,
Some of those games they really.
All right, whatever. I tried my argument. Okay, okay. Look at all the ones that you said were trees. Is there a special term that we can use for each edge in that tree? Huh? you say ranch?
She said ranch. No, she said, no,
Ranch.
she said ranch.
It begins with a B.
Bridge.
What?
Bridge.
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 Why can't it be branch? I mean,
Yo.
that's the same thing. And it's a tree.
Vertices and one edge of a bridge.
Okay, so every edge in a tree is considered a bridge. There is only one line that connects two dots. So when removed, it creates a disconnected graph. So, reiterate, your job is to connect all of your vertices with one edge and one edge only. You should never have more than one edge connecting two dots, ever. It's not lies. Okay, this is your last term.
That's crazy.
Crazy.
This is our what?
This is your last term for today.
Oh, term, okay.
Term.
Notes.
Spanning tree. A spanning tree is a subgraph of a network that connects all vertices and has no circuits. A subgraph of a network that connects all vertices and has no circuits.
So it's unique.
Okay, so the easiest way to create a spanning tree is to first count your amount of vertices.
1, 2, 3, 4, 5.
Thanks, Rodrigo. Rodrigo says 1, 2, 3, 4, 5. So if I have 5 vertices, to connect them, I would need how many edges?
4.
I found that.
1, 2, 3, 4.
So you need to, I know you do not have a lot of space, so you're only going to be able to put one example here. You need to use all 5 of your dots and connect them using 4 edges.
Oh, it won't face out.
So
B to A.
A to B, B to C, C to D, D to E. That is a spanning tree. There's no circuits and everything's connected. Okay? I'm going to draw you another one. If you want to squeeze it on there, you can. I know you don't have a lot of room.
Yeah, that's it.
There's another one.
Some crisscross. Wait, hold up.
Here's another one. There are multiple ways to do this.
Oh no,
You say?
I screwed up.
You did.
Wait, what did
You say?
Tomorrow we're going to learn a formula on how to determine how many spanning trees you have in a picture.
Bruh, why did I?
Why?
It's really not that bad.
I'm just gonna.
Really not that bad. I promise. Okay, so this is a summary of everything we've talked about. So remember, in order for it to be a tree, you have to have one more vertex than you have edge. You need to have one and only one path that joins two dots. You need, every edge has to be a bridge. You have to have a tree. Oh, we already talked about that. Okay. So this is the section that you're going to hate.
No, I would love it.
Okay. So what I'm going to do is this is your homework tonight. Because Listen, I know you're going to struggle with it. I know you are.
Maybe not. I mean, you can just do it.
But maybe not, maybe you're right, maybe not. Okay, so these 8 problems, you need to look at the problem and tell me, it will always be a tree, no matter what you do. If you would try to draw that picture, it would always be a tree. It would never be a tree. Or sometimes you could draw a tree using that situation, and sometimes you could not. Okay, so to help you out, I'm going to tell you right now, there are 3 that are always. There are 3 that are never. And there are 2 that are sometimes. I want you to 100% try this on your own. Tomorrow, we will talk about the whys they are, or the why they're not, or the why it's sometimes. Okay, so when you finish this,
Done.
okay, you can work on your chapter 6 project. I'm gonna go over it real quick. You can update your websites. I'm going to go through your data tracking folders, and if there's issues with it, I'm going to pull you and tell you what to do to fix it, so they're ready. Do not forget, your student-led conference letters must be turned in tomorrow. Okay. You said run that back?